The objective of this lecture is to provide examples in rigid body kinetics. The first problem is as follows. A circular disk of radius r rolls without slip along an inclined plane where the inclination of the plane is beta. The incline is inertially fixed and gravity acts downward. The center of the disk will be denoted by C, and the angle that the disk forms with the normal to the plane is denoted by theta, where we place a point P on the edge of the disk such that the angle between that normal to the incline and the direction CP is theta. Now, point Q is the point of contact of the disk with the incline, and there's no slip at the point of contact. So the objective here is to determine the differential equation of motion of the particle in terms of the angle theta. So let's write that down. The objective is determine the differential equation of motion for the disk in terms of theta. Now, we also have to stipulate here that the radius of the disk is r, and that the mass of the disk is m. Okay, so this is how we're going to do this problem. We actually can see in this problem that we need two coordinate systems. So this is really important. We need to apply Euler's laws, and we're gonna apply Euler's laws in this problem in a couple of different forms. But in order to do that, we need to first figure out the acceleration of the center of mass and the angular momentum of the disk relative to the center of mass. And in order to do that, we need to set up coordinate systems. So we're going to use two coordinate systems in this problem, and I'll draw them over here. The first coordinate system is going to be one that is aligned with the direction down the incline. I'm going to call this direction EX. And then EZ is going to be into the page, and then EY is going to equal EZ crossed with EX. Now this basis is going to be fixed in the ground with the origin at point C when t equals 0. And the second coordinate system is going to be a principal axis coordinate system with its origin at the center of the disk. Remember, this is C and this is P. I'm going to call the direction along CP, I'm going to call it ER. I'm going to call it EZ again into the page, and E theta is equal to EZ crossed with ER. Now what's really important here is don't get misled that this is a horizontal and vertical direction, these ER and E theta. It's fixed to the disk. So this is fixed in D with origin at C. Now, in order to be able to do this, we need the following. We need the acceleration of the center of mass and the angular momentum relative to the center of mass of the disk. So the first thing we need to start with is we need to figure out the acceleration of the center of mass. So the way we're going to do that is as follows, is that the disk rolls without slip along the ground. So that no slip condition implies that the velocity of the point of contact, the instantaneous point of contact on the disk and the ground, has to equal the velocity of point Q on the ground. in the ground. But that velocity of point Q on the ground is 0. So as a result, the velocity of point Q on the disk in the ground is equal to 0. And now, from the kinematic relationship between the velocity between 2 points on a rigid body, we know that the velocity of point C, which is equal to the velocity of the center of mass, is equal to the velocity of point Q plus the angular velocity of the disk in the ground crossed with R bar minus RQ. Now, if you actually look at this, you'll see that the velocity of the center of mass is then equal to, well, the velocity of point Q is 0. The angular velocity of the disk in the ground is equal to theta dot Ez, and the position of the center of mass relative to point Q is equal to minus R Ey, because Ey is pointed down and to the left. So this gives R theta dot Ex. That's the velocity of the center of mass. And as a result, we get that the acceleration of the center of mass is equal to R theta double dot Ex, because Ex is inertially fixed. Next, we know that the angular momentum relative to the center of mass is equal to the moment of inertia tensor of the disk multiplied by the angular velocity of the disk in the ground. Now, this principal axis coordinate system, we're going to actually, we identified it this way. This, suppose I let E equal ER E theta Ez. We note that E is a principal axis basis. And as a result, we have the following, that if I express the inertia tensor of the disk in this basis E, that's equal to, I get 3 principal moments of inertia relative to the center of mass. And then all the off-diagonal elements in this matrix representation of this tensor are 0. Now, for a uniform circular disk, the following is true. I r bar equals I theta bar equals mr squared over 4, and I z bar equals mr squared over 2. And then furthermore, we know that when we express the angular velocity of the disk in the ground in this basis defined by E, we get 0, 0, and theta dot, from which the angular momentum of the disk relative to its center of mass expressed in this basis E is going to equal the following. Well, if we multiply this out, we get 0, 0, mr squared over 2 theta dot, which when we put this back in vector form gives us mr squared over 2 theta dot Ez. So that's the angular momentum. So now we have the acceleration of the center of mass and the angular momentum, and now we can apply Euler's 2 laws. We have to draw the free body diagram in order to be able to start the kinetics of this problem. So the free body diagram is as follows. Here's the disk, and here are the forces that are acting on the disk. There's a normal force, there's the force of gravity, and then there's a force that's caused by the rolling without slip. I'm going to call that force R. Now let's identify these forces. We know that N is in the direction of EY. We know that R is in the direction of EX. Now again, I don't know whether they're positive or negative, so I just assume that they're positive because I don't know either of these two forces. We also know that MG lies in the direction of the unit vector that's vertically downward. And if you look at the unit vector that's vertically downward, you can actually see that if we draw it over here. There's the unit vector vertically downward. This direction is EX, and this direction is EY, and the angle formed between U and EY is beta. So from this we actually get that the unit vector vertically downward is equal to sine of beta times EX plus the cosine of beta times EY, from which we can actually write that mg is equal to mg sine beta EX plus mg cosine of beta times EY. So then we can apply Euler's first law. So Euler's first law, if you remember, says that the force is equal to the mass times the acceleration of the center of mass. Well, the force is equal to N plus R plus mg, and that has to equal the mass times the acceleration of the center of mass, which gives Ney plus Rex plus mg times the sine of beta Ex plus mg times the cosine of beta times Ey, and that has to equal mr theta double dot Ex. So if we break this up further, we've got mg times the sine of beta plus r times Ex plus mg cosine of beta plus n has to equal mr theta double dot Ex. So therefore, when we write this out, we get mg times the sine of beta plus r has to equal mr theta double dot, and we get mg times the cosine of beta plus n has to equal 0. So these are the first two equations. Now, for Euler's second law, we actually have a couple of choices. We're going to do this actually using the center of mass, because the center of mass is always the most convenient point. So if we use the center of mass as the reference point, we have the following, that the moment relative to the center of mass is equal to the rate of change in the ground of the angular momentum of the center of the angular momentum of the center of mass. The rate of change in the inertial frame, which is the ground of the angular momentum relative to the center of mass, is equal to mr squared over 2 theta double dot Ez. And because Ez is inertially fixed, there's no second term in the transport theorem. In order to be able to compute the moment relative to the center of mass, we have to go back to the Freebody diagram. If we actually look at the moment relative to the center of mass, we can see that mg and n go right through the center of mass. So we wind up with the following result. We wind up with rq minus r bar crossed with r is the moment. That's equal to rey crossed with rex, which is equal to minus little r times big R times Ez. So as a result, we get that mr squared, or actually we'll do it in the same order, we get minus rr times Ez equals mr squared over 2 theta double dot Ez, which gives the third equation, and that third equation looks like this. Minus r times r equals mr squared over 2 theta double dot. Now, we can actually take these equations and we can now solve for the differential equation. So first, solve 3 for r. What do we get when we do that? We get r is equal to minus mr over 2 times theta double dot. Now what we can do is we can substitute that result into 1. So substitute r into 1. What do we get when we do that? We get mg times the sine of beta minus mr over 2 theta double dot is equal to well actually we got to be careful here. We got mr equals mr. Let's copy this correctly. mr theta double dot. So this gives 3 halves mr theta double dot is equal to mg times the sine of beta, which gives theta double dot is equal to 2/3 g over r times the sine of beta. Now that's the differential equation. Now I'm going to do this problem using one other method. And this second method uses the instantaneous point of contact. So we're going to use the instantaneous point of contact as the reference. Now the way this is going to work as follows is that we know that the instantaneous point of contact is an arbitrary point. So as a result, we know that the rate of change in the ground of the angular momentum relative to point Q is going to equal the moment relative to point Q minus r bar minus rq crossed with MAQ. Now we have to figure out all these things. So the first thing I'm going to do is I'm going to compute the angular momentum relative to point Q. Well, we know that that is related to the angular momentum relative to the center of mass from this relationship that was derived in the process of shifting angular momentum from the center of mass to an arbitrary point. So this, of course, we have mr squared over 2 theta dot ez, which is what we got for the angular momentum, plus now rq minus r bar is equal to rey crossed with m. The velocity of point Q is 0, and the velocity of the center of mass is minus r theta dot ex. So this gives mr squared over 2 theta dot ez plus mr squared theta dot ez, which is equal to 3/2 mr squared theta dot ez. So that's the angular momentum relative to point Q. Now, the next thing we need to compute is we need to compute the moment relative to point Q, and we need to get this additional term. Well, if this is the angular momentum relative to point Q, then the rate of change of that angular momentum, because Ez is inertially fixed, we get 3/2 mr squared theta double dot Ez. And again, the second term in the transport theorem is 0 because Ez is inertially fixed. So now I have the rate of change of the angular momentum. So next, the moment relative to point Q is equal to, if we go back to the Freebody diagram, we'll actually see that the moment relative to point Q is due purely to gravity because the other two forces go through point Q. So this is equal to r bar minus rq crossed with mg. But that's equal to, I might put it on this line, it's equal to r bar minus rq is minus rey crossed with mg times the sine of beta ex plus mg times the cosine of beta times ey, which gives that the moment relative to point Q is equal to mgr times the sine of beta times ez. Ey crossed with the x is negative ez. So that gives me the moment relative to point Q. And finally, we need to compute, we need minus r bar minus rq crossed with MAQ, and we need to compute the acceleration of Q. So the acceleration of point Q is equal to the acceleration of the center of mass plus the angular acceleration of the disk in the ground crossed with rq minus r bar plus the angular velocity of the disk in the ground crossed with the angular velocity of the disk in the ground crossed with RQ minus R bar. Now this is equal to R theta double dot EX, which is what we had derived before, plus theta double dot EZ crossed with R EY, and then plus theta dot EZ crossed with theta dot EZ crossed with R EY, which is equal to R theta double dot EX and then minus R theta double dot EX. Now EZ crossed with EY is minus EX, and then EZ crossed with EX is EY, so we get minus R theta dot squared EY. So as a result, we get that the acceleration of point Q in the ground is equal to minus R theta dot squared EY. So then, minus R bar minus RQ crossed with M, A, Q, and G is equal to minus, well, R bar minus RQ is minus REY, so this gives me REY crossed with M times minus R theta dot squared EY, which gives me 0. So that additional term in this case is equal to 0. So then we obtain the following results. We have that 3/2 mr squared theta double dot, that's the rate of change of the angular momentum, is equal to mgr times the sine of beta. And actually, forgot the EZ here. EZ is equal to mgr sine beta EZ plus the, or minus the additional term, or plus the additional term, which is 0. So this, if we simplify it, we get 3/2 mr squared theta double dot is equal to mgr times the sine of beta, which simplifies to theta double dot is equal to 2/3 g over r times the sine of beta, which is the same differential equation we obtained using the first method. So we've done this with two methods, one using the center of mass, one using the instantaneous point of contact, and we got the same differential equation in both cases. So now what we're going to do is we're going to move on to another example. The next example that will be studied in this lecture is as follows. In this problem, we have a semicircular cylinder. So the way this is going to be portrayed is as follows. We have a semicircular cylinder which rolls, which moves while in contact with the ground. It's not rolling. Now, the way I'm going to portray the semicircle is I'm going to draw the full circle, and then half of the cylinder is going to be with mass. So the bottom half of the cylinder has mass, and the top half doesn't have any mass. The center of this full cylinder is going to be located at point O. The center of mass is located at point C, and the distance from the center, geometric center, to the center of mass is going to be labeled B. Now the angle that's formed by the vertically downward direction and the direction along OC, that angle is going to be defined as theta. And here, because there's slip, there's going to be some friction, and we're going to use, in this particular model, we're going to use viscous friction. And the friction coefficient is going to be C. Now, the coordinate that's going to describe the translation is going to be x, which is going to be the displacement of the geometric center of the cylinder. And the radius of the cylinder is going to be denoted r, and the mass of the cylinder is going to be m. So remember, this is a semicircular cylinder. Half of the mass, or half of the cylinder, has no mass. So I'm just going to label that here. There's no mass in this half of the cylinder. The cylinder. Okay, now the objective of this problem is to determine, forgot to mark that there's gravity acting downward. The objective of this problem is to determine the differential equations of motion for the cylinder in terms of x and theta. Now, again, we have to apply Euler's laws. So we're going to start this whole process off by determining the acceleration of the center of mass and the angular momentum relative to the center of mass. We're going to use two coordinate systems to solve this problem. I'm going to draw the coordinate systems on the next page, and we're going to redraw this picture. So there's the semicircular cylinder. Now, point O, like I said, is here. We're going to put a direction EX to the right. I'm going to put EY down. EZ is going to be into the page. And then the origin of this, so this is fixed in the ground, and its origin is at O when x equals 0. Now the next coordinate system that I'm going to have, now this gets a little tricky, so I have to be a little careful here. The basis is going to be such that the direction from, let's make these the same size just to make sure that everything is sort of aligned nicely. So this is O and this is C, and the direction ER is going to be along OC. Now, so this is the direction from O to C. Now, what's important here is that ER is along OC, EZ is again into the page, and then E theta is equal to EZ crossed with ER. But what's a little bit tricky and a little confusing here is that we need two coordinate systems. We need one to describe the position of C relative to O, and the other one we need to describe the angular momentum relative to the center of mass. So there are actually two coordinate systems here. So both these coordinate systems are fixed in the body. But the difference is there are two different origins that I'm going to be using in two different contexts. So the origins are at O and C. And I'll get into why we need both of them in just a minute. Okay, so the way we're going to do this is first I need the position of the center of mass. So the position of the center of mass is going to equal the position of point C relative to where O is when x equals 0, because that's my inertially fixed point. That's equal to the position of C relative to O plus the position of O relative to where O is when x equals 0. The position of C relative to O is equal to B times ER. The position of O relative to where O is when x equals 0 is XEX. So that's the position of the center of mass, and again, all distances have to be measured from an inertially fixed point. That's why in one of the contexts for this basis ER, E theta, EZ, I need to measure from point O, because notice that I need to measure from point O in order to get the position of C relative to O. So that gives me, that's the first context in which I'm going to use this basis ER, E theta, EZ. The velocity of the center of mass in the ground from this then becomes, well, now we can actually do this a couple of different ways, but the easiest way to do this is just to apply the transport theorem. If we do that, we're going to get, so we can write this as XEX plus BER, and then you can, XEX. Now, if we take the rate of change, we get X dot EX, and then we have the rate of change of BER. But the rate of change of BER is going to be the rate of change of BER in the body plus the rate of change, plus the angular velocity of the body crossed with BER, which when we're all done is going to give B theta dot E theta. And that just comes from the transport theorem. The acceleration of the center of mass is then going to equal X double dot EX, and then we're going to get plus b theta double dot e theta, and then again plus theta dot ez crossed with b theta dot e theta, which gives minus b theta dot squared er, and that's from two applications of the transport theorem, which gives the acceleration of the center of mass is equal to x double dot ex minus b theta dot squared er plus b theta double dot e sub theta. So there's the acceleration of the center of mass. Now, the second context in which I'm going to use this basis, er e theta ez, which is fixed in the body, because notice I said it was fixed in the body, is to compute the angular momentum relative to the center of mass. In order to compute the angular momentum relative to the center of mass, I need a body fixed coordinate system, and it should be a principal axis body fixed coordinate system in the context in which we're doing these problems, and its origin has to be at the center of mass, which means its origin has to be at point C. This is equal to the moment of inertia tensor of the body relative to its mass center multiplied by the angular velocity of the body in the ground. Now, if I use the center of mass as the origin, the moment of inertia tensor of the body expressed in that basis. So let's call E equal to ER E theta EZ. If I'm measuring from the center of mass, this gives me this is a principal axis coordinate system, and the moments of inertia relative to the center of mass are IR bar, I theta bar, and IZ bar. Now, the angular velocity of the body as viewed by an observer fixed to the ground, again expressed in this basis ER E theta EZ is equal to 0, 0 times and then theta dot, which gives that the angular momentum relative to the center of mass when expressed in this basis is going to equal, well, we get 0, 0 and then IZ bar times theta dot. Now, these quantities IR bar, I theta bar, and IZ bar are constant, so it doesn't really matter what they are. So I'm just going to leave it in terms of IZ bar. It's a constant, and so I can substitute a value in, but it's not going to really help in terms of understanding the process for this problem. So I'm just going to leave it. I'm going to leave it, and we're just going to keep it. We're going to keep it as IZ bar. Now, given that, this tells me that the angular momentum in vector form is equal to IZ bar times theta dot times EZ. So now I've got the acceleration to the center of mass and the angular momentum relative to the center of mass, and now I can go ahead and start with the kinetics. So let's draw the free body diagram. So the free body diagram, in this case, here's my semicircular cylinder, and then of course this thing's oriented at an angle, and here's the center of the cylinder. Here's the point O. Sorry, there's the point O. This is the point Q, which is the point of contact, which probably should have labeled it right at the beginning. I didn't. I should have labeled it as Q. That would have helped a little bit. And then the forces that are acting on this body, at the center of mass, I have gravity acting downward. So here I have mg, and then, and actually, you know, let's just make this bigger. Let's exaggerate this a little bit, mg. And then here I have a rolling force. Sorry, not a rolling force. I have a friction force because there's viscous friction. And then here I have a normal force. Now these are the things that I have to figure out. A couple of these are actually fairly straightforward. mg is equal to mgey because it acts vertically downward. N is also equal to ney. And again, it doesn't matter whether I make this positive or negative because I don't know what the coefficient n is. The friction force is the hard part. The friction force is equal to minus c times the velocity of the point of contact on the body as viewed by an observer fixed to the ground. And since they're sliding in this particular case, this velocity is not going to equal the velocity of that point on the surface because I can't apply the no-slip condition. So we have to use 2 points on a rigid body in order to be able to get the velocity of point Q on the body B in the ground. This is equal to the velocity of O in the ground plus the angular velocity of the body in the ground crossed with RQ minus RO. This is equal to x dot ex plus theta dot ez crossed with r ey, which is equal to x dot minus r theta dot ex. So that's the velocity of point Q on the body in the ground. And then from this, I can actually compute the friction force. The friction force is then equal to minus c times x dot minus r theta dot times ex. So there's my friction force. So now I can start applying Euler's two laws. So Euler's first law, it says that the force is equal to the mass times the acceleration of the center of mass. The force is equal to the gravity force plus the normal force plus the friction force, which is equal to, well, if I sum all these, I get n plus mg ey minus c times x dot minus r theta dot ex, which gives that the force, if I put it in the order of the basis vectors, is minus c times x dot minus r theta dot ex plus n plus mg ey. And that has to equal the mass times the acceleration of the center of mass, which is equal to mx double dot ex minus mb theta dot squared er plus mb theta double dot e sub theta. So the equation that I get when I'm all done here, I got minus c, let's put it all on one line, x dot minus r theta dot ex plus n plus mg ey is equal to mx double dot ex minus mb theta dot squared er plus mb theta double dot e sub theta. Now we can get differential equations sort of in this context, but the easiest components to deal with this are ex and ey. So if I take f and I take its dot product with ex, I get minus c times x dot minus r theta dot. Now that has to equal the mass times the acceleration of the center of mass dotted with ex. And that equals mx double dot minus mb theta dot squared er dotted with ex, and then plus mb theta double dot e theta dotted with ex. And you can see that that's the first differential equation. So if we actually look at the picture, I can draw the picture. Let's see, maybe I can draw that now. It's probably better to draw the picture. Let's draw the picture over here. So we have ex, we'll draw it on the other page, which is we have ex, we have ey, we have er, and then we have e sub theta. Now, this angle here is theta. So, if you look at the picture, er is equal to cosine of theta ey minus the sine of theta times ex. And then e theta is equal to, because this direction here is negative ex and this angle is theta, we get that e theta is equal to minus the cosine of theta times ex, and then minus the sine of theta times ey. So if you look back over here, we need er dotted with ex. So er dotted with ex is equal to minus the sine of theta, and e theta dotted with ex is equal to minus the cosine of theta. So therefore, we have minus c times x dot minus r theta dot is equal to mx double dot, and then we have minus mb theta dot squared, and then er dotted with ex, which gives you plus, and then the sine of theta, and then the other one is plus mb theta double dot, and actually there's a negative sign that's going to come in, so I'm going to just put the negative sign in there, minus mb theta double dot times the cosine of theta. Now that's the first differential equation. So we now have the first differential equation. And we now need to get the second differential equation. Well, the second differential equation is not going to be quite as easy. We have to do a little bit more work. The first thing we need to do is we need to actually finish the process with taking dot products. So if I take f dotted with ey, that gives me n plus mg, and that has to equal, well, if I take the dot product with ey, I get minus mb theta dot squared er dotted with ey, and then I get plus mb theta double dot e theta dotted with ey, which gives that n plus mg is equal to, I've got er dotted with ey. Well, I take er dotted with ey, that gives me cosine of theta. And I'm just doing that from looking back up above at the earlier expressions. If you take er dotted with ey, you see that it's cosine theta. And then you get plus mb theta double dot e theta dotted with ey. E theta dotted with ey is minus the sine of theta. So that flips the sign here. And so we get minus mb theta double dot. And then e theta dotted with ey, as I said, was minus the sine of theta. Now, why do I need that? I need that because this is going to show up in Euler's second law. So I'm going to use this equation in Euler's second law. We're going to save it for right now. Let's just keep it handy. Let's call this equation star, and we'll use it in just a minute. So let's apply Euler's second law. So Euler's second law, if I use the center of mass as the reference point, says the moment relative to the center of mass is equal to the rate of change in the ground of the angular momentum relative to the center of mass. Well, the rate of change of the angular momentum is equal to, because Iz is constant, we got Iz bar times theta double dot times Ez. And again, there's a transport, but the second term in the transport term is 0. So that's all I have for the rate of change of the angular momentum. The moment relative to the center of mass, now we need to go back to the free body diagram. So if you look at the free body diagram, you'll see that point C, which is the center of mass, is where the force of gravity acts. So gravity doesn't create a moment relative to the center of mass, but the force of friction and the normal force both do. So this becomes RQ minus R bar crossed with, since both these forces act at point Q, the moment is applied at the same point. So RQ minus R bar is equal to minus BER plus REY. Now how did I get that? Well, I got that because if you look at the diagram, here's point C, that's the center of mass, there's point O, and then there's point Q, right? This distance here is B, this distance is R, this direction is ER, this direction is EY. So in order to get from C to Q, I got to go in the minus ER direction by a distance B, and in the positive EY direction by a distance Q. And I'm sorry, this should be an R. REY. My apologies. So that is RQ minus R bar, and then I've got crossed with minus C times x dot minus R theta dot EX. That's the force of friction, and then plus N EY. Now this, if I take the cross product, I get plus BC. Let's just get rid of the plus sign. So I get BC, and then I've got x dot minus R theta dot, and then I've got ER crossed with EX. That's the first term. And then the second one gives me minus B times N times ER crossed with EY. And then I have minus C times R times X dot minus R theta dot. And then EY crossed with EX gives me plus EZ. And then the last term is 0. EY crossed with EY is 0. So this, now I can compute these. ER crossed with EX. Well, what's ER? ER is equal to minus sine theta EX, and then plus cosine theta EY, and then that is crossed with EX, which is equal to EY crossed, which is minus cosine of theta times EZ. And then I also have ER crossed with EY. ER crossed with EY is equal to minus the sine of theta EX plus the cosine of theta EY, and now it's crossed with EY, which is equal to minus the sine of theta times EZ. Now what does that give us? That gives us that the moment relative to the center of mass is equal to, I've got BC times x dot minus r theta dot, and then ER crossed with EX, which is equal to minus the cosine of theta times EZ. That's that term. And then I have minus BN ER crossed with EY. ER crossed with EY is minus the sine of theta, so this gives me plus BN times the sine of theta times EZ. And then plus CR times x dot minus r theta dot times EZ. So this moment becomes the following. It gives me CR times x dot minus r theta dot, and then I get plus BN times the sine of theta and minus BC times x dot minus r theta dot times the cosine of theta. The whole thing is multiplied by EZ. And that has to equal the rate of change of the angular momentum relative to the ground, which is equal to IZ bar times theta double dot times EZ. So the equation that I'm going to get, if I start combining things, I can take the x dot minus r theta dot and I can combine it. So what I'm going to get is I'm going to get x dot minus r theta dot. This whole thing gets multiplied by CR, and then I've got minus BC. So actually the C comes out too. So I can actually put the C in front of the whole thing. So let's just do that. Let's put the C in front of the whole thing. So I've got C times x dot minus r theta dot, and then I've got times, and then this gives me r, and then I've got minus b times the cosine of theta. That's what I have in that expression, plus bn times the sine of theta has to equal IZ bar times theta double dot. Now, what I can do is I can substitute in the expression for n. Remember I had that equation from a while back? So we can solve for n. So let's solve star for n. And what do we get when we do that? We get n is then equal to minus mg, and then if I get minus mg minus mb theta dot squared cosine theta, and then I get plus or minus mb theta double dot sine theta. And if I substitute that into this last expression, that gives me C times x dot minus r theta dot, and then that times r minus b times the cosine of theta, and then I've got plus b times n, and n is equal to minus mg minus mb theta dot squared cosine theta minus mb theta double dot sine of theta. This whole thing is multiplied by the sine of theta. So actually, let me give myself a little bit of room here so I can write this out a little bit smaller. So this gives me plus b times minus mg minus mb theta dot squared cosine theta minus mb theta double dot sine theta times the sine of theta, which is that term there, equals iz bar theta double dot. Now, it's not a very, a great looking differential equation, but that is the second differential equation. So this becomes the second differential equation. Okay. So that's the end of this particular problem. And now we're going to move on and we're going to do a third example. So the third example is the following problem. Is suppose I have an arm. I'm going to do this with it's an arm, a uniform slender arm of mass m and length L, and it rotates about the vertical. So I'm going to try and draw this as best I can. Okay, so it rotates about the vertical, and I'll show the rotation as follows. So there's the vertical direction, and it rotates in such a way that it's relative to the ground. It rotates with an angular velocity omega relative to the ground. So this is a massless shaft, and then the center of the arm is at point C, which is inertially fixed in this case. The angle formed by the arm with the horizontal is beta, and the arm has mass m and length L, and like I said, C is the center of the arm. And the objective of this problem is to determine, assuming that there's only a torque applied to the body, so there's going to be a torque applied to this body, what is the torque required to maintain a constant angular velocity? So what is the pure torque, or just torque, required in order to maintain a constant angular velocity? So what that means is, that means that the magnitude of omega, which is equal to omega, should be a constant. Now in this particular problem, there are no forces that are applied to this body. The only action that's going to be applied to the body is going to be a torque. So in order to do this problem, we don't even need to worry about the center of mass, because you can see the center of mass is an inertially fixed point, and because of that, F equals ma bar applied to the center of mass, the force applied to the body is going to be 0. So the only coordinate system I need in this particular case, since I don't need to describe the position of the center of mass and then subsequently its acceleration, I need a principal axis coordinate system to describe the angular momentum of the body. I'm going to make that principal axis system, I'm going to call it ER along the arm. I'm going to call EZ is going to be out of the page. Well, it's not out of the page. It's actually normal to the plane of the shaft and the arm. And then E theta is equal to EZ crossed with ER. Now this is fixed in the body with origin at C. Now what's important to note here is that this is a principal axis basis. These directions, two of these are in the plane of the shaft and the arm. The other one's normal to the plane of the shaft and the arm. Now, because the center of mass of B is inertially fixed, that implies that the acceleration of the center of mass, which is equal to the acceleration of C, is equal to 0, which implies that the force applied to the body has to be 0 from Euler's first law. So we don't even need to worry about Euler's first law. That's why I said Euler's first law is not relevant in this particular case. Okay. Now, so we have to apply Euler's second law. So Euler's second law looks like this. If I apply it relative to the center of mass, it says the moment is equal to the rate of change in the ground of the angular momentum as viewed by an observer fixed to the ground relative to the center of mass. But the angular momentum relative to the center of mass is equal to the inertia tensor of the body multiplied by the angular velocity of the body in the ground. And the inertia tensor of the body expressed in this body fixed basis E, which is the only basis I've defined here. So we're going to call this thing E. This is equal to IR bar, I theta bar, IZ bar, and then all zeros. And then the angular velocity of the body in the inertial frame is the next thing that we need to compute. So we can see that if we look back, you see that omega is about the vertical direction. So this is the direction of omega. This is the direction of ER. This is the direction of E theta, the way I had it defined. And then this angle is beta. Now because this angle is beta, that means that this angle is also beta, right? So as a result, what we get is we get that omega is equal to omega cosine beta minus omega sine beta. So minus omega times the sine of beta times ER, and then plus omega cosine of beta times E sub theta, because this direction is minus ER, right? So it's cosine beta times E theta, and then sine beta times ER. So this gives us the angular velocity, which means that, and that is equal to omega bg, which means that if I express omega bg in this principal axis coordinate system, I get the following: minus omega times the sine of beta ER, and then I get plus omega times the cosine of beta in the E theta direction, and then I get 0 in the EZ direction. So now, when I'm done with that, that tells me that the angular momentum relative to the center of mass, when I express it in this basis, is going to equal, well, let's see what it's going to equal. I've got IR bar, and then that's going to be multiplied by omega minus omega times the cosine of beta. And then I have I theta bar, which is going to be multiplied by omega. The first one's multiplied by omega sine beta. And then this is multiplied by omega cosine beta, and then 0. Now note something. In this particular case, IR bar is equal to 0 because it's a uniform slender rod. And I theta bar, which is equal to IZ bar, is equal to ML squared over 12. So as a result, the angular momentum, when expressed in this basis E, is going to equal 0, and then I'm going to get ML squared over 12 times omega times the cosine of beta, and then 0, which gives that the actual vector form of the angular momentum is equal to ML squared over 12 omega times the cosine of beta times EY. Now, I have to compute the rate of change of this angular momentum. I have to do that in just a bit because I have to apply the moment equals the rate of change of the angular momentum. So the moment is equal to the torque that I'm trying to figure out. And now we need the rate of change in the ground of the angular momentum relative to the center of mass. Let's compute that. So the rate of change in the ground of the angular momentum relative to the center of mass is equal to, well, it's equal to the rate of change of the angular momentum as viewed by an observer fixed to the body, plus the angular velocity of the body in the ground crossed with the angular momentum, and that's from the transport theorem. This first term is equal to 0. Why is it equal to 0? It's equal to 0 because omega is going to be constant. We said we needed a constant angular velocity. Everything else in that expression is constant, so that's 0. But the second term is not 0 because I have the angular velocity of the body in the ground, and that's equal to minus omega sine beta ER actually I called it ER, so let's call this should be E sub theta, so not E sub y. So this is equal to, it's still equal to 0, but that should have been called E sub theta. And then I've got, so now let's go back and get this angular velocity. I got minus omega sine beta ER plus omega cosine beta E sub theta crossed with the angular momentum, which is ml squared over 12 omega times E sub theta, which gives the following. It gives that I've got minus omega sine beta ER plus omega cosine beta E sub theta. Okay, let's go back. Let's just make sure we grab that minus omega sine beta ER. So now ER crossed with E theta is equal to EZ. This gives ml squared over 12 times omega squared with a negative sign times EZ. But that has to equal the moment relative to the center of mass, which is equal to the torque, which implies that the torque required in order to maintain a constant angular velocity is minus ml squared over, and there's a sine of beta that's missing. Sine of beta EZ times omega squared times the sine of beta times EZ. So this is the torque required to maintain a constant angular velocity omega. So that means that the magnitude of omega, which is equal to omega, is equal to a constant. All right, that's the result. Now you can actually see something interesting, is that as beta goes to 0, the sine of beta also goes to 0, which means that as the arm gets aligned with the horizontal, this torque also goes to 0, which means and the reason is because the direction becomes a principal axis direction when beta is equal to 0. When beta is not equal to 0, it's not a principal axis direction, and as a result, this torque is not 0, but when it is a principal axis direction, the torque is 0. So we've studied 3 problems in this video, and these 3 problems have shown different aspects of using rigid body mechanics. And in the next lecture, we'll add to this by studying a few more examples, which will round out the sort of the variety of problems that one might typically see when studying the basics of rigid body mechanics.